Okay, so let's work this problem. So we're going to have to construct the influence line, and then we're going to have to compute the maximum negative moment created at A due to a uniform dead load and a live load. So the first thing we need to do is calculate the moment at A. How do we calculate the influence line for the moment at A? So how do we do that? Well, let's begin by examining the structure. So I'll draw a free body diagram, and we'll see what we've got. So I'm curious in the bending moment at A, and then I have a reaction over here at C. And I also have a reaction here at A. Now the problem is I have three unknowns, and I really only have two equations. Summing forces in the x direction gives me nothing. So this is really kind of indeterminate in this form. So I'm going to have to do what here? I'm going to have to break it apart here in the center. Everybody see that? So let me redraw it here. So I'll have one free body with my moment at A, my reaction at A, and then I'm going to have, I'll just do it in shear, so I'll have the shear at B here, and then of course on the opposite side, the same shear at B, different direction, equal and opposite, and then my reaction at C. So there's conceptually what I need to do. Now remember, my goal is to find the moment at B. Okay? So in one scenario, looking at my tube, I'm going to come back and I'm going to say, well, let's just assume initially that my unit load can be anywhere between x and 5. That means just between A and B. So it'd be somewhere, what, here, right? Won't be on this side. It'll be on this side. So I'll go ahead and locate it there. That's x. This would be 5 meters. This side is 10 meters. So the distance here would be 5 minus x from the cut, if I need to know that. So as I solve for the, I'm going to look at these two free bodies and solve for the moment in A, and that will be valid for my unit load between 0 and 5. Now, what's the shear at B here? Well, if you look at the right-hand side free body, what are all the forces there? They're 0, right? You see that? There's no applied force, right? So the reactions are 0. If I sum moments about C, what's the reaction at B have to be? 0. So in this particular case, I don't have to worry about it because these are all 0. So if it's 0 here, it's 0 there, and now this free body gets a lot easier to solve. So I'll sum moments where? About A, make sure it's in equilibrium. And when I sum moments about A, what do I have? I don't care about AY because it passes through A. I have my moment, which in this case is negative. And I have the unit load at a distance of x. It also creates negative moment. Force is 1, distance is x, and of course we just know that shear is 0. So what's the moment at A equal to? Looks like it's negative. Oops, I wrote 1. It should be negative x, right? Are you buying that? I hope you are, because it's right.
Why are you using the dead and live load instead?
Have it. That's the application part. The first thing we're doing is drawing the influence line for the moment at A.
So you can touch them to the end pretty much?
Don't touch them to the end. So what's the situation when we go from 5 to 15? That means my unit load is here somewhere. So in that sense, what free body do I use? Well, I'll come here and show you. I'll redraw these just the way I did before so you can see the difference. So the right-hand side, I still have my reaction at A. I still have the moment at A. I'm assuming I have this shear at B, equal and opposite. And I have my reaction at C. But now my unit load is here. You guys see that? This is still 5 meters. This is still 10 meters. Oh, not X, meters. I'm still trying to find the moment at A. So how do I do that? But the only way I can do is if I sum moments at A in this free body, my moment at A is equal to whatever I get for my shear at B. So how do I get my shear at B? Probably some moments about C. What's this distance here going to be? Now remember, yeah, the total distance from A to the load is X, so this bit's going to be 15 minus X, right? So this is going to be a two-stage one. First, I will sum moments at C, and when I do that, I'll get the unit load creating positive moment at a moment arm of 15 minus X. Then I'll get the shear creating negative moment, and its moment arm is 10. So I can solve for the shear at B. Looks like it's going to be 15 minus X divided by 10, right? There's the shear at B. Any questions about that? So now if I know the shear at B on this free body, I know the shear at B here, and now I can find the moment at A. So next I will sum moments at A equal to 0. Here, let me just do this. It might help. I'll call this free body 1, free body 2. This is from free body 2, and this equation is going to be from free body 1. Just have to keep track of them. So now when I sum moments about A, I get the internal moment A, which is negative. And then I get the shear at B, right, times a moment arm of 5. So that I can solve for the moment at A. It's going to be the shear at B times 5. So what's that end up being? Looks like it's negative. Multiply this by 5. The 5, this makes it 2. So it looks like I get 15 minus X divided by 2. Okay? Now I just need to plot it so you can visualize it. So I'll do it over here. I think I can squeeze it in here. So this is the moment at A. It's a function of X. And I want to do it at 5. There's 10 more. So from 0 to 5, I plot this. That starts off at 0, and at 5 it ends up being what? minus 5. Right? And then from 5 to 15, I plot this equation. You put in x equal 5, what do you get? 10 over 2, which is minus 5. It matches. And then if I go all the way over to 15, it's what? 0. So there's my influence line for the moment at A. And just to put the dimensions on there, don't forget this is 5 meters and 10 meters. I saved a little space way up here at the top. It's going to look funny because looks like we did this first, but this actually comes last. Let's solve the problem. So first let's look at the single live load of 10 kilonewtons. Where do I put that on my structure to create the maximum moment at A? Well, I put it right here at 5 meters, right? Because the maximum value is 5. I did leave off the units here. This is in meters. So my concentrated load, my concentrated live force is equal to 10 kilonewtons times what? Minus 5 meters. That gives me a negative 50 kilonewton meter moment. So that's the moment at A when the 10 kilonewton force is at 5 meters. That's the maximum moment. It starts off at 0, goes up to a maximum of 50, and then it decreases back to 0. So that's the maximum. What about the dead load? What's uniform? And we just learned that the way you find the effect of uniform load is you take the magnitude of the load, which is 1.5 kilonewton meters, times the area under the curve. So the dead uniform load is equal to the intensity, which is 1.5 kilonewtons per meter, times the area of this curve. It's a triangle. The area of a triangle is 1/2 the base. The base is 15 meters. And what's the height? Minus 5 meters. So the units are still going to be kilonewton meters, which is moment. I don't know what that's going to be. You guys have to help me with that. 1.5 times 7.5 times 5. 56 point something? What?
6.25.
Anybody else get 56.25? Is anybody else out there? Hello, China. Are you there? Oh, sorry. I was thinking of my F-15 fans from a few years ago. See if they're watching my video again.
6.25.
So I lost track. What? 56.25?
Yes.
Okay, so 56.25, and that's also kilonewton meters. But I have to add it together. So the maximum moment at A would be, you add those two together.
Oh, wouldn't that be negative?
Oh, thank you. So you're going to add those two together. Looks like you get 106.25. And also negative. So that's the maximum moment at A due to a dead load of 1.5 kilonewtons per meter and a live load of... And just to show you how this would work, that means that the load would look something like this. I'm putting the dead load over the whole structure, and the concentrated load is right here over 5. So that's the distribution. The dead load is over the whole structure, and the live load, the concentrated force, is right there. That combination creates the maximum moment of A. Now the dead load can't do anything about it. It's everywhere, right? But the concentrated force does move. But at that position, that's where it creates the maximum moment of A. Okay, that problem took 15 minutes. 15 minutes, the magic 15-minute barrier. Any other questions?
Why was BB 0?
Why would what be 0?
Why was BB 0 for the first diesel column?
I didn't hear you say it again. Why is what 0?
Shear at B and C1.
Why is the shear? Okay, look at this free body here. Some moments at C. What's the shear at B have to be equal to?
Okay.
Plus, there's no forces. Usually, when there's no forces applied to the structure, it has nothing to react to. So all the forces are 0. All right.
No problem.
Now, that's not true in reality, because in reality, a structure has self-weight and it's reacting to its own weight. Remember, we're not considering self-weight in any of our structures, except for your project 2, where you are considering self-weight. Okay.